The application of the equilibrium equation have been studied since the engine static, and then we use this in the mechanics of material. The procedure is simple. There is one important step is to draw the free body diagram of the structure or structural member. By drawing the free body diagram first, we supposed to set up the reference axis of the x and y since after we finish the free body diagram, we got to use summation of x of x equal to 0 and summation of f of y equals to 0. So we will know which direction is x and which direction is y. And then we draw the known forces and moments. And next, we draw the unknown forces and moments. And finally, we put some length and angle into the free body diagram. And in the drawing of this structure, we supposed to consider the A is the pin and the C is also the pin. Under application of the 2000 Newton force, we have 4 unknown. If we consider the whole structure, we have the 4 unknown reactions. And then we have only one free body diagram. And then we have 3 equations of equilibrium. That means we cannot analyze this structure. So we need to separate the structure into 2 parts. And then the unknown is going to be 2 at A, 2 at C, and 2 at B. The total unknown forces is 6. And then the number of equations of equilibrium that we have is 3 times 2 members of AB and BC is only 6. So that means this way we can analyze this frame. One more thing we supposed to notice from the engine static. The member AB is so special. You may need to recall if the member of structure have the pin or hinge connection and there is no forces or moment along its length. What we call this member is called the two forces member. And if the AB is two force member, the free body diagram of the beam BC can be simplified by the two force member, the force F sub AB going to apply into the joist B with the angle of 60 degrees. And then the beam going to have only 3 unknown forces. And if we compute this problem going to be a lot easy. There are 3 equations of equilibrium to find the reactions on the member BC. Which one we are going to use first? Actually, we always use summation of moment. This time, we take the moment at C. So C sub x and C sub y will be eliminated from the equation. And then we can find the F sub AB easily. After we take the moment, and then we find the F sub AB, finally, we use summation of F sub x equal to 0 and summation of F sub y equal to 0 to determine the 2 more unknown. Okay, let's come up to the task. For the task shown here, The A is the pin and the G is the roller. They ask us to find the reaction at the A and the G. And for the force in the member DE, EH, and the other we will talking about is later in the next chapter. Anyway, before we find the reaction by drawing the free body diagram of the thrust and use the equation of equilibrium, let us review something about zero force member. What is going to be some zero force member? There is two rules. One, if two members is connected together and no force act at that point. For example, the EF and the FG connect at F and no force at F. These two members are going to be two zero force members. And the second law, if there are three members connected together, two are in parallel, and there is no force acting at the joints, the third member gonna have zero force. Okay, that's for the review. And then we can draw the free body diagram of the thrust. Let me repeat again. Free body diagram is the shape of the structure that are free from the support. When we draw it, first we put the reference axis of x and y, and then we sketch the whole thrust. And next we put the no force to the structure, and then we put the unknown forces. The A is A sub x and A sub y, the G is just G sub y. And the last part of that, put the length that are important. Over here is 4 meters. Over here is 4 portion with 4 meters each. The total is 16 meters. And then if we like, we use the equation of equilibrium. Just take the moment at A. So the A sub y and A sub x are eliminated from the equation of summation of moment A. So we have counterclockwise as positive. So the G sub y times 16 is positive. And then the moment due to the light blue forces going to be the clockwise, so they are going to be negative. The 30 will times 0. The 20 will times 4. This 20 will times 8. This 40 will times 12. So all of that are negative. And plus G sub y times 16. You get G sub y of 45 kilonewton. And then we use summation of x sub x equals to 0, since there is no horizontal force. A sub x is 0. And the last one, summation of f sub y is 0 and point up is positive. So A sub y plus 45, which is G sub y, is positive. And minus 30, 20, minus 20, minus 40, we got A sub y of 65. Is this make sense? Yes, it makes sense. A sub y is larger than G sub y because most of the forces are on the left hand side. You should have some this kind. You should have checked by using this kind of sense. This makes sense. Most of forces near the A, so the A sub y is larger than the G sub y. Okay, we go to the next example of the beam. For this beam, the A is the pin, the C is the roller. The beam subjected to uniformly distributed load between AB and also the moment at B. And then we draw the free body diagram after we set up the X and the y, x is horizontal, and y is in vertical, we get the a sub x and a sub y at A. And for the roller at C, we got C sub y. And then we made summation of x sub x equal to 0. A sub x is 0. And if we take moment at C, the a sub y gonna rotate clockwise. And then we set the counterclockwise is positive. So a sub y times 10 is going to be negative clockwise. And the force 2 kilonewton per meter gonna have the resultant here. The magnitude of it is going to be 2 kilonewton per meter times 5 meter is going to be 10 meter. And the resultant going to act at the centroid of the area, which is 2.5 meter apart. And the moment due to this resultant force will rotate counterclockwise, so it is going to be positive. And 2 times 10 gonna times the distance. Over here is 2.5 and then plus 5. And 50 kilonewton meter rotate clockwise, so it is negative. Putting them into the calculator, we get a sub y of 2.5. And then the summation of f sub y equal to 0. C sub y plus a sub y of 2.5 is going to be minus 10. So the c sub y is 7.5. So it's easy, right? And we have this as the final free body diagram of the beam. Next, we come to the beam that is more complex than previous one, because that previous one is for the static. For this beam is for the theory of structure. This beam has the locker at A and C and the pin at B. It's subjected to 3 forces and has the joint at D. So by analyzing this, the total unknown is 1 at A, 2 at B, 1 at C. The reaction are A sub y, C sub y, B sub x, and B sub y, total of 4. And since the D is a joint, so the reaction is going to be 4 plus 2 is 6. Total is 6 unknown. And if you consider the beam can separate into A, B, D, and D, C, so the number of equation of equilibrium going to be 3 times 2 is 6. So this structure is statically determined. And when you draw the free body diagram of this beam, you got to separate them into 2 pieces. The first one is a DC. For the DC, the C going to have C sub y, and D is the hinge is going to have D sub x and D sub y. When D sub x and D sub y in this direction, when you draw the beam ABD, the D sub x going to be in opposite direction and D sub y going to be in opposite direction. This follow the third law of Newton. And then B sub x and B sub y and A sub y. So the total unknown of the beam ABD is 5. So we're going to start by considering the free body diagram of beam CD. The beam CD has 3 unknown. Okay, and then if you take the moment at D, we're going to find the C sub y. The C sub y gonna rotate counterclockwise about D, and C sub y gonna times 4. That is going to be positive. The 7 kilonewton force must be separated into the vertical direction. It's going to be 7 sine 60. And in horizontal direction, it's going to be 7 cosine 60. So only 7 sine 60 produce the moment that in opposite direction of the C sub y. The 7 sine 60 gonna time this distance of 1. and it's going to be negative. And c sub y times 4 is positive. You got c sub y of 1.52. And then summation of f sub y equal to 0, d sub y plus 1.52 and minus the red force. This is 7 sine 60. And then you got d sub y of 4.55. And for the d sub x and the blue force is 7 cosine 60 degree. They are in opposite direction. So the d sub x is 3.5. When you have the d sub x and d sub y, put the d sub x and d sub y into the portion ABD. So this is 3.5 and this is 4.55. This free body diagram of the beam will have only 3 unknowns. Okay, and by doing this, we start by summation of moment at A equal to 0. So the B sub y will rotate counterclockwise, and B sub y will times moment arm of 8. The horizontal force, all of them produce 0 moment since it's passed through the point A. And then 16 kilonewton going to be negative by timing 4. 6 kilonewton produce negative moment by timing of what? 10 meter. And 4.55 also produce the negative moment time of what? 4, 6, and 8 is 14. So we get the b sub y of 23.5. And then we can determine the a sub y by summation of f sub y equal to 0. Up is positive, so a sub y is positive. 16 negative. 23.46 is up, positive. Minus 6 and minus 4.55. We get the a sub y of 3.09. And the last one, summation of x sub x equal to 0. B sub x is equal to 3.5 kilonewton. Okay, guys, this beam is worth for the theory of structure. I like you guys to concentrate on a more complex beam for this course, right? And if it is a simple beam, the load applied on it is going to be more complex than before in the engineering static. Okay, coming to the frame. Now we have the frame. This frame have the pin at A and the pin at C. This frame separate into 2 portions. First is ADB. At the B is the hinge. Okay, and then connect to the member CEB. If we consider the total reaction of the whole frame, we have 2 at A and 2 at C. And if it is only one free body diagram, 4 unknown is larger than 3 equation of equilibrium. So we got to separate this frame into 2 portions. And then we have unknown A 2, C 2, and B is 2. The total unknown is 6. And there are 2 free body diagram. 2 times 3 equation of equilibrium is going to be 6. So the number of unknown is equal to the number of equation of equilibrium. Okay, and we separate the free body diagram into this portion and this portion. It should be noted that the force at the hinge B are in opposite direction and the magnitude of them are equal. When we take a look at this free body diagram, How do we solve for 6 unknown reactions? The best way is using the equation of equilibrium with the moment equal to 0 at A. If we take the moment equal to 0 at A, we will write the equation for the unknown forces of B sub x and B sub y. We get one equation. And then we take the moment at C again. We get another equation with the unknown B sub x and B sub y. With 2 unknown and 2 equations, we can solve these 2 equations simultaneously to get B sub x and B sub y. After we know B sub x and B sub y, we can find the reaction A sub x and A sub y, and also C sub x and C sub y easily. And also, we can determine the internal forces at E. Okay, let's start. We use the summation of moment at C equal to 0. So this time B sub y produce the moment, and B sub x produce the clockwise, which is in opposite to this. So B sub x times t is going to be negative. And the uniformly distributed load here going to have the resultant force of 1.5 times 3, the area of the load. And it acts at the centroid at the middle of the member CEB. So B sub x times t is negative, so it is clockwise. 1.5 times 3 is going to times this length of 1.5 is positive because it's rotated counterclockwise. So B sub x is 2.25. When B sub x is 2.25, put this force into the red arrow here. We got this 2.25. So the free body diagram of member ADB gonna have only 3 unknown. We take the moment at A again. So we take one here. We will find the B sub y. Again, the B sub y have the line of action here, which is 3 meters far away from A. The 3B sub y gonna be clockwise, so it's going to be negative. 2.5. 2.5 have the line of action here, and the line of action are 3 meters from the A. 2.5 times 3 is going to be positive. B.5 times T is going to be negative. Okay, so B.5 times T is negative. 2.5 times T is positive. For the angular force, the resultant of the force is 1/2 times the length 3 and 2 kilonewton per meter, and it acts at the centroid of the triangular, which is 1 meter from A, and it's rotated clockwise, so it's negative. We get the B sub y of 1.25. So now this guy is 1.25, and if this is 1.25, so over here is 1.25 B sub y, and then we can determine the A sub x easily, A sub y easily. You can do it by yourself. Okay, and also this is 1.25. We can get this is 1.25. And how about C sub x? For summation of f sub y equal to 0, the C sub x gonna be 2.25. Okay, and then if you like to find the internal forces, it's gonna be easily just cut it at, so example as E, there are normal force, shear force, and moment over there. Okay, guys, I'm finished the application of equation of equilibrium here. We will use this equation of equilibrium a lot in the later portion of this subject. And now we have the homework for chapter 2. that you guys supposed to work by yourself. Try to use the knowledge, develop your skill. The important thing is there is 1, 2, 3, 4, and the rest of this is 2 key dash 25 dash 27 and dash 39. I like you guys to use the program structure. Try to exercise it. I put the manual into the zip file already. Just study the manual. The program are designed in a way that even the high school student can use the program. So I hope you guys can do it by yourself. And if you have problem, our teaching assistant are ready to help you. And you got to put these 3 problems into the system. The main thing is the result of the reaction that you obtain will be equal to those you obtain by manual calculation. If not, don't turn in. Try to solve the problem until you get the same solution. Alright? Okay, we finish the chapter 2 here, and again the chapter 2 will appear in the first problem of our midterm examination, and the problem divided into 2 parts. The first part is talking about the force or load distribution, one-way action or two-way action, and the second part is going to talking about the determinacy and stability of the structure. I upload the midterm examination of the last year to the Google Classroom. So I like you guys to try to do it. I think that is a good reference. If you can do it clearly, correctly, you are going to be in a good position. If not, just do some practice on that. Okay? The theory of structure is easy, but it's only require you to pay more attention, to spend time with problems, to make you guys get skills on the free body diagram and also for the equation of equilibrium. Okay, let's end this chapter now, and we will move to chapter 3 later. Bye.